Welcome one and all. Welcome back. Super psyched to have you here. I think it is time. So today we are going to start actually legit doing optimal control. We spent, our first couple of weeks doing a nice little gentle introduction to, dynamics and how to discretize them, and then control, then optimization, how to do basic optimization stuff. And now I think we are ready to dig in. So to sort of set the stage and have a little bit of a palate cleanser, kind of get us out of the intro phase and into the meat of the class. I wanted to kind of do this little history lesson thing and maybe give you a bit of a tour of, historical tour of some of these topics, hints at what's to come, just as a little, fun thing. Ask questions, whatever. So a brief history of control. Click. In the beginning, there was the Christochrone problem. Has anyone heard of this before? Someone who's heard about this. What is this thing?
Like the one. It's the shape that maximizes the speed of the velocity of the ball.
Yeah, so it's the minimum time curve for a ball sliding down a ramp. So you say I have point A, point B, what B being lower than A, and I want to make a track or a ramp or whatever connecting those 2 points such that a ball released at point A will land at point B in minimum time. As who knows what the solution to this is?
Cycloid.
A cycloid, yeah, which is a weird, not obvious thing at all, right? So which one of those shapes is fastest is the question, right? So yes, do you know the history of this? Anybody? It's a fun history problem. So this was like posed as a challenge to the math physics community in what at the time would have been a journal, basically, by one of the Bernoullis. There are too many Bernoullis. I don't know which Bernoulli, but one of the Bernoullis. And it was posted as a challenge problem in one of these journals, proto journals in the 1690s. And it was solved independently by a bunch of people, Newton, Leibniz, and L'Hopital among them. But Newton's solution is the most famous one, is the one we still remember, because it actually laid the foundations of a whole bunch of what became modern optimal control theory. So this is the solution written out in modern notation. This is how you get it. You're minimizing this cost function thing, which is the total time, but you basically can write this down as minimizing this integral cost function thing, right, along a trajectory, which is very much the flavor of trajectory optimization kind of stuff that we're going to do. And Newton basically invented what's called calculus of variations now, this idea of minimizing functions and stuff like this, which we're going to do a little bit. He basically invented that to solve this problem. And we still use it and stuff, so which is kind of cool. And the solution turns out to be this shape called a cycloid, which is the shape you get if you trace out a point on the rim of a circle as it rolls. Which is kind of weird and super not obvious and super not intuitive, and you would have never guessed this, but it turns out that's the optimal shape of the ramp here to get this minimum time solution for a ball rolling down the ramp. Kind of weird. Okay, so this was kind of that solution, and it turns out that led to this entire kind of little subfield of mathematics called calculus of variations, which we're going to talk about a little tiny bit here, but generally avoid. Because the math gets a little gnarly, and I find it's generally just not that necessary for doing practical stuff. But it's the subject of basically minimizing continuous with respect to continuous functions. So all the optimization we did was minimizing basically with respect to finite dimensional vectors, like some x in Rn. Here you're minimizing some continuous function x of t, which is a little weird. And we're going to talk about that today and some of the implications of that. But turns out, right, so he did it for this, minimum time problem, which very much has the flavor of an optimal control problem. But the math is useful in tons of other applications, ranging from statics. So it turns out it's also how you get the shape of a hanging cable or chain or something. Optics, it's Fermat's principle. If you've heard of that, it's very much this kind of minimum time flavor. Classical mechanics, this is Hamilton's principle, least action, how you get the Euler-Lagrange equations for Lagrangian mechanics. Finite element methods, this is the so-called weak form that you use to develop FEA methods in mechanical engineering. It's also general in GR, it's kind of the standard approach, and it's one of the several approaches to doing quantum mechanics, the so-called path integral approach. So it shows up in a ton of areas of physics, in addition to what we're going to talk about, optimal control, kind of useful, kind of interesting. So that's where that comes from, and that's one of the sort of like foundational little subtopics of what we're going to talk about. And then sort of moving forward in time, another thread. Does anyone know what this thing is? Yeah. So it's called a centrifugal governor. And do you know what it does? Can we describe, anyone describe what it actually does? Yeah.
So it uses those masses to control the speed, pretty much by changing its inertial properties with the speed.
Yeah. So like the way I would describe it is, so you have like some spinning, the output shaft, say, of a steam engine. And if you wanted to spin at constant velocity, roughly speaking, what will happen is those two masses will get pulled outward like this under centrifugal force as it spins faster. And this thing's hooked up to a valve that opens and closes to like to basically the throttle on the engine, right? So the sort of mass of the ball counteracts, the speed of this thing spinning around, and it sort of settles into this. And it like, as they're pulled upward, right, it closes the valve more. As they fall down, it opens the valve more. It basically controls the throttle, right? So this thing is very clever. It was invented by Christian Huygens, another famous like physics name, and was used shortly thereafter by James Watt on the first steam engines in like the 1780s. And this was like one of the big things in the first industrial revolution. It enabled like all these kind of steam engines, locomotives, trains, blah, 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 all this kind of factory stuff. Huge part of like the industrial revolution, right? So it was invented in the late 1700s. And this is feedback, right? This thing is doing feedback control in like a mechanical mechanism. But no one like actually theoretically modeled this or understood the math behind it for like another century. The first paper that actually worked the math out on this came about 90 years later in 1868, and was by another famous physics name, James Clerk Maxwell. So Maxwell of Maxwell's equations from electricity and magnetism wrote the first paper analyzing this in what we would call modern, basically developed all the math that in that paper that you would see in any of your standard undergrad courses on feedback control. So like all the SISO, root locus, Bode, Laplace transform stuff, all of that is in this 1868 paper by Maxwell. And it's actually amazingly readable. It's on the internet. You can find it on like archive.org or whatever. And it's like, it looks like a paper that you would read now, basically. And like all the math is there from your like undergrad, SISO controls course. Kind of a fun, if you're a nerd and you're like, this kind of thing, I actually highly recommend Googling that paper, like Maxwell steam governors or whatever. It's kind of crazy how readable it is from like 1868. And like you would be familiar, if you've taken an undergrad controls course, you would like understand all of that. It's really funny. Yeah.
And then a lot of music classes have one of these for error.
Oh, cool.
Yeah, they use error resistance.
Yeah, okay, that's super fun to like get the speed to be the same. Yeah, that's very clever.
It's like a flat thing.
Yeah, cool. Okay. So that's fun. So that Maxwell paper was basically the first paper to do what would be called classical control theory. From there, you get into the so-called like classical control era, right? Which is like kind of early 20th century, leading up to like kind of just past World War II. Tons of cool stuff was done in this period. A lot of it before there was any theory. Which honestly, this kind of reminds me of like where we're at right now with deep learning. Like so much of this stuff is like, we're just trying stuff before we have real theory. So the first autopilot for an airplane is this guy. That was 1914, doing like kind of PID control with like hand-tuned gains that no one really understood if it was going to be stable or not. The other thing that was done around this time was the first basically autopilot for a ship was done in 1911. All this was kind of basically PID. And then starting in the 20s, you started to see this stuff get formalized, and there started to be theory. So like all the stuff you basically learned in your undergrad, kind of frequency domain, SISO controls class, that was all developed. So like Nyquist, all those famous names, those were 1920s roughly, when all this stuff was formalized and theoretically analyzed, and people figured out how to like guarantee stability of these things. And a lot of that work was done actually in the context of vacuum tube amplifiers in EE. So like a lot of that stuff was EE stuff, but back then people were doing this kind of thing. And then this all took a huge leap forward because of World War II. You want to know that right picture is? That's a V2. So this was like the first rocket that reached space. It was built by the Nazis in World War II. And a big part of this is solving the so-called rocket problem, which is how you get a rocket to go straight up and not like go nuts and fall over and crash. Rockets are inherently unstable. You can think about it as a big inverted pendulum. So in order to get a rocket to actually fly, you need to do basically digital feedback control on the rocket nozzle at the bottom. So the whole rocket engine gimbals. And this thing's basically a giant inverted pendulum. So early rockets, there's tons of blooper reel footage of rockets from like the 40s and 50s going like all kinds of crazy and crashing and stuff. Most of it has to do with control, actually. So it's an inverted pendulum, but it turns out it's a floppy inverted pendulum. They're big enough that they're light enough that they're very flexible. There's a lot of like unmodeled dynamics in the flexible modes of a rocket. And so there's a lot of early work on this frequency domain control stuff and trying to make rockets work. And a lot of that was done in World War II and kind of the years shortly thereafter, which leads us up to the so-called modern control era, which started right around 1960 with another famous name I'm sure many have heard of, which is Rudolf Kalman of Kalman filter fame. So it turns out Kalman, basically around the same time, developed both the Kalman filter and the corresponding control theory, which is LQR, which is all kind of the same math. So that kind of checks out and makes sense. And essentially where that came from, why it's a thing and everything. So before this is kind of this CISO frequency domain Laplace era that you would have learned in an undergrad control class, which is really pre-computer math, right? And then what happened in this era that like really made the difference was computers came along, and you could actually, like every university had a computer in the basement beginning around this time. And so it started to become possible to solve large matrix equations pretty easily. And then you had the Apollo program, which was a major impetus for doing more digital computing stuff and more stuff in control. And that's a picture of the Apollo guidance computer. That's the thing that actually flew on the Apollo missions to get you to the moon. So it's like this big-ish and was a legit computer that could do floating point math. And so this let people actually do kind of the stuff we do now, right? So Kalman developed the so-called state space methods using lots of linear algebra for doing what we're going to do very soon. And that sort of all started happening in the 60s. It was enabled by having computers, but it also opened up doing way more complex control. So basically all the old school EE type CISO stuff in the frequency domain really only worked for single input, single output systems very well. Whereas this stuff, now you're talking about large multi-degree freedom systems you can handle with big matrices, which, you know, rockets flying to the moon and robots, right? High degree freedom robots. That's sort of all enabled by computers being able to do large matrix math. Funny story. Does anyone know the story of the original Kalman filter paper? This is, Kalman couldn't get it published anywhere, got rejected like everywhere. And it ended up getting published in some obscure journal because he could not get it published in any of it.
Proceedings, I believe.
Yeah, it got
all the EEs rejected.
That's right. He was like an EE math guy and he couldn't publish in any of their journals. And it ended up getting published in some like second tier mechie journal because he couldn't get it published anywhere else, which is hilarious. And then also this time, so all that stuff happened. And then really because of Apollo, that the Kalman paper was like 61, maybe the original Kalman paper. And then a guy named Schmidt, who was working at NASA Ames, basically was tasked with figuring out how to navigate to the moon, and like went home for a weekend, read the Kalman filter paper, and invented the extended Kalman filter and the square root Kalman filter, like in a weekend, to fly Apollo to the moon. And then went into work on Monday with the answer. And they coded it up and made it work on that box, and we flew to the moon. That's basically the story. So that the extended Kalman filter is often called the Kalman-Schmidt filter, because the original Kalman paper is for a linear system, right? And obviously flying to the moon is a nonlinear problem. So so we figured out, you know, the extended Kalman filter where you basically linearize, right? And whatever, and do it on a nonlinear system. And that's history. And that was done only a few years after the original paper. And then they flew it to the moon in 69, you know, like a couple of years after that. So kind of insane. The pace of what happened in that period is a pretty amazing. The other thing to mention is in parallel with all this, so that's like the American side of the story. Also, at the same time in the 60s was this a couple other parallel developments. One was in the Soviet Union, they also had a space program and were also doing things. And there, the big name is Lev Pontryagin. Has anyone heard of this guy? Pontryagins maximum or minimum principle, which we're going to talk about today. So that was happening in the Soviet Union around the same time. And they were interested in optimizing rocket trajectories or missile trajectories or whatever. And so that's kind of, that theory is developed around there. And then in the US, There's Richard Bellman also at the same time, late 50s through the 60s, doing dynamic programming, which you probably also heard about. So that was all kind of in the same, within a decade, all of that happened, which is pretty nuts. Okay, cool. So kind of also, that was the 1960s was when all this stuff was kind of really done. Kind of, you know, around the same time / later, there were a few other kind of things that kind of went with this. One of which was adaptive control, which is concerned with like online adaptation to unmodeled things, also known as online learning, maybe in RL. These are the same thing. This is, you know, two examples of this. This is a really old example from the late 50s, early 60s, the X15, where they actually did a bunch of this stuff. They literally were doing online gradient descent on the control policy on that thing with a pilot in it. And someone died actually in 1967 when one of these crashed because they didn't understand the closed loop stability of this thing while it was doing online gain tuning learning. And then this is kind of a modern example of this, right, on a quadruped doing the deep learning version of this, but it's really the same stuff. The online adaptation stuff, they were doing it on, linear feedback policies in the 50s with online gradient descent with various learning rules. And now we're doing it on, deep neural network policies, but it's the same stuff, like to a remarkable degree. And if you talk to some people in the modern field who are doing this stuff, they'll tell you that, like, that it's really kind of the same ideas, but now we're basically doing it on just bigger policies because we have more compute, right? Yeah. So there's a direct lineage from that, late 50s stuff to like current, like modern sort of online RL kind of algorithms. What else? Oh yeah, this is great. So, okay, robust control. This is so we have adaptation, right? We were trying to like adapt online to mismodeled things, whatever. The other big thread that came out, this is one of the best control theory papers of all time. You're all reading it. I'll tell you about it in a sec. So this is robust control, which really started up in the 80s. And coming off of like the high of, LQR, Kalman filter, all this great stuff, people for a while thought in the 60s and 70s thought that like LQR, you can prove mathematically that LQR on its own has some natural robustness properties. Like it's naturally robust to mismodeled dynamics. So in this case, in a linear system, your A and B matrices, if there's some errors in those things, you have unmodeled dynamics. Turns out LQR you can prove that it has some really nice natural robustness properties to mismodeled stuff. But it turns out, and John Doyle, who's still around, he's a professor at Caltech, he wrote this when he was a grad student. It was his first paper. Insane. So basically what he proved was that if you take a LQR controller and a Kalman filter and you hook them together, so you have a closed loop LQG thing with both the Kalman filter, the state estimator, and the controller, that can be arbitrarily brittle, like arbitrarily sensitive to small model mismatch, and that it has like no provable robustness whatsoever. And so what he basically did in this paper is provide a couple of counterexamples showing that you could write down a couple of systems with an epsilon in them in the A's or B's, such that epsilon for any non-zero epsilon, infinitesimal epsilon, the thing would go unstable, which is kind of interesting. So this paper basically founded an entire branch of control theory called robust control, linear robust control, where people started looking at how do we develop closed loop control systems like this, where we can guarantee robustness to like bounded model errors. So the flavor of a lot of this work is I have this A and B, the nominal A and B. I'm going to say, I can bound the error in A and B by, 10, 20%, or like polytopic bounds on the entries or something like this. And given those bounds, I can now generate a feedback policy that is guaranteed to stabilize any system in those bounds, so that when you go online, you can guarantee the thing's not going to be super brittle and blow up on you. So that was kind of a lot of the work in the 80s into the 90s in control theory was focused on this set of ideas. This kind of robust stuff was very hot for a while. Now there's a MATLAB toolbox that will just do it for you. It's called H-infinity control. Yeah, cool. So but this paper's amazing. Like, it's also like 2 pages long. It's like 2 counterexamples. There you go. Kind of awesome. Let's see if this will work. Okay, model predictive control. We're going to spend a lot of time in this class about this. This sort of started in the 70s. The idea here is you can solve an optimal control problem numerically. We're going to do a lot of that in this class. Well, if you can solve it really fast, you can just do it online. And that's your feedback policy. You just keep resolving the optimal control problem numerically. If you can do it really, really fast at, say, 50, 100, 1,000 hertz, then that's all you need. You don't need any other kind of feedback policy. That's the key idea. And this really unsurprisingly also tracks with the history of computing. Basically, like the idea is you're going to solve, you just numerically brute force solve this optimal control problem at real-time rates. So this only really became possible as computers got fast. It started in the 70s, actually, in chemical engineering. So, which actually has a long history and connection to CMU, which, yeah, whole other conversation. But basically the reason it started there is that chemical plants are slow. You only need to run your updates on your control policy like once every 30 seconds or something, really slow dynamics. So you could do this on an 80s vintage desktop computer, no problem. Just solve the control problem. If it took 10 seconds to solve, that's real time, you're good to go. So it kind of started there. It started to creep more into robotics applications in the 2000s. In robotics, we need to run a lot faster, obviously. So as computers got faster and faster, we started being able to do these things at tens of hertz, hundreds of hertz. In some instances, you can now solve decent size optimization problems for this kind of thing at kilohertz rates. So we can now do this stuff on quad rotors, and like literally every robot ever is doing MPC now, just about, right? So this is how we do driving, you know, walking, parkour on Atlas, drones, pretty much everything's doing MPC now because the computing has gotten fast enough to just solve it, right? Yeah, cool. So this is state of 5 years ago, state of the art, right? Like being able to do this kind of thing in real time. You can see you can throw obstacles in there and it'll resolve around the obstacles, all kinds of fun things. We're going to do this in class. So you'll learn how to do this, at least in sim on a real deal quad rotor. Cool. So this is fun stuff. We're going to spend a lot of time on this. What else? Okay, so parallel stuff that was going on in robotics around this time, like in the 80s, which we're not really going to talk about in here, but which you've probably heard of, is stuff on like industrial manipulators on arms like this. It turns out the control methods here are way, way different than what we're going to do and what like kind of was happening in the control theory community. And there's a big reason why. These things are what we call fully actuated. They have the ability to supply torque on every single joint in the system. So you can basically make this thing do whatever you want all the time. And if you think back to the mathematically, what this corresponds to is, if you remember the manipulator equation that we talked about when we talked about dynamics, and most of you seen know this stuff really well. So you got mass matrix, right, Coriolis thing, and then your BU control input thing. What this means is that this B matrix that maps controls into the dynamics is full rank and invertible. And what that means is, if you want to know what your controls should be, in this context, because of this fully actuated thing, I can literally just write down an arbitrary trajectory, a Q of T, and then I can just invert this guy and figure out what the controls are to do that. So it turns out for these industrial manipulators, the control problem is basically trivial, and there's not a whole lot of stuff to do. That said, there are a bunch of 80s vintage papers on this in the robotics community doing things like what are called operational space control and things like this. But they're all basically just invert the V matrix and write down whatever you want, and it just works. So there's not a ton of interesting control there. There isn't, more now, but this is kind of coming from the robotics perspective now. This stuff wasn't that interesting, at least from my perspective, but it does work. Cool stuff is, though, here. So this is also started in the 80s, legged robots. So this top left guy is from the CMU leg lab, which became the MIT leg lab, which is Mark Raybert, which became Boston Dynamics. This is what they were doing in the 80s, which is awesome. These hopper robots, super cool, super dynamic, and also super underactuated, right? This thing's reasoning about its balancing and all its dynamics in a really sophisticated way. So this stuff's super cool. Same time was in Japan, Honda and Waseda University were doing these humanoids with bipedal walking. Also really cool, but using very, very different approaches. So the Raybert stuff is doing stuff that I would say is like very much in line with the kind of things we're talking about. And currently what BD is doing is very much the stuff we're talking about, where you're reasoning about dynamics and doing a lot of optimization stuff. Then it was like a lot of hand-tuned stuff. But that's where it was like a lot about the dynamics, right? The passive dynamics of the system. Whereas the Honda approach is very much rooted in this. They were basically trying to use the same techniques that you used on an industrial arm to control this guy. And you can see it really visible in the differences in how these things look. This guy's doing backflips. This guy's walking like a robot, right? Like the classical walk like a robot thing. And that's because what they're basically doing is it has really big honked feet. And they're basically saying, whenever a foot's on the ground, I'm going to pretend this thing is a fixed base manipulator like an industrial arm. And I'm going to do the, invert B trick to control it. And I'm, as a result, not reasoning at all really about the dynamics. And so I'm walking super slow so that I don't have to reason about balancing or, any of that stuff. And like you can model it as a as basically an industrial arm is what's going on there. So if you know the more recent history of these things, you can kind of tell which approach won out. The bottom right kind of peaked in the early 2000s with Osimo, which probably a lot of you have seen. That doesn't really exist anymore. And obviously, like the Rayboot approach resulted in Boston Dynamics, which now we see lots of. And so that's kind of the history of that. There were kind of these two schools of, legged robots for a long time. Okay, so yeah, our stuff is going to be more of the backflip variety and less of the industrial arm variety. Cool, legged robots. What else? Oh yeah, and then just to kind of fast forward, hint. Why is this not working? Right, so this is fast forward a few years, and this is what everyone's doing. BD, Cheetah. So BD and Cheetah are both doing MPC online, which is we're going to talk about explicitly in the class. We're actually going to do some stuff on legged robots later in the class, pretty explicitly, tell you basically how Cheetah works. And then there'll be a homework assignment on one of the last homeworks. You'll do some legged robot stuff and optimize some gates for a biped and stuff. And if you want to do any projects in these kind of areas, you're very welcome to. There's lots of cool things to do there. MPC wins.
For the jumping robot, like which joint is underactive? Like all the joints are.
So underactuated means that at any instant in time, you can't control all of your degrees of freedom. So for a floating base legged robot, you're always underactuated. You may have motors in all your joints, but your floating base degrees of freedom, like the body, you don't have instantaneous control over that, right? You can only control the body via, exerting forces against the world, right? And so that's always underactuated.
That is true for the other one, right? Like,
Which one?
the one that is moving so.
Oh, yeah. So it's true here too, but what you're doing is you're basically, whenever you have one foot on the ground, you're modeling as if that foot is bolted to the ground and I have an industrial arm. And so you basically are simplifying a whole bunch of things down in terms of what you're doing with the controller so that you can reason about it like that, which results in these very robotic looking walking behaviors that just aren't very dynamic, right? And whatever. And it's because of that. It's because of the control techniques they're using. Yeah, it is definitely an underactuated system. They're playing tricks with how they operate the robot, basically, to like make it mostly fully actuated. So if you have one foot on the floor and it's a really big foot, then you can basically pretend it's fully actuated as long as you don't do anything super dynamic. If you're like this in the air, underactuated completely. And so there's lots of the other thing where you'll become in that situation, you'll see Osimo, if you ever watch, always walks like this with its knees bent. It's because of this. If you straighten your knees out, you become underactuated because there's a kinematic singularity there, right? So that makes you underactuated. So you can, like, by watching these things, you can kind of pick out a lot of these little details that are like coming from shortcuts or tricks people are playing in the controller to avoid sort of having to reason fully about the dynamics like this. Those kinematic singularities, if you're doing MPC, if you're doing this optimal control stuff, you just don't care. It doesn't matter. But if you're doing this kind of like invert the B matrix thing, well, if you straighten your knees all the way out, B becomes not invertible and then you can't do that, right? So, okay. What else is in here? Yeah, so that's a bunch of cool stuff. We're going to talk about a lot of this, just kind of history stuff. Last, like, little notes from me. Challenges for the future. Contact is always hard. So like all this manipulation, walking stuff, super hard. We kind of mentioned that before. Another big one that, like, I think you guys collectively in the room really have a chance to like dig into. And I think my advice to you is there's a big gap right now between people who do MPC and model-based things and people who do RL. And I don't think there should be. But there is this historical divide there. And there are very few people who speak both languages and know both fields well enough to sort of cross that gap. And if you want to make an impact as a researcher right now in this area, I would suggest getting really good at both sides and speaking both languages. There's like a huge amount of possibility in between there. And right now there are too few people who know both sides who can actually bridge the gap. So long-term, I would suggest maybe thinking about that as a career move. And yeah, so part of that is, right now RL is famously inefficient data-wise and needs too much data. MPC stuff doesn't need any data. So I think there's like a lot of in-between possibilities there, right? Of like bridging these things to make RL more data efficient, stuff like that. A perennial, one that dates back to this kind of robust control stuff is giving safety guarantees. You can do it for linear systems, but those aren't very interesting, practically speaking. So safety guarantees on like uncertain nonlinear system, everything, right? Cars, et cetera. Especially cars is a big deal, right? Cars and airplanes, it's a really big deal because you have people in them. But being able to give any kind of safety guarantee, you're not going to like hit the pedestrian or whatever. These are big deal kind of things, right? So if you can make a dent in that problem, huge potential impact. And then another one that's kind of fun is also relevant to driving, dealing with other possibly adversarial agents, right? So like reason about the behavior of other humans or other autonomous cars, right? If you're out on the road, this becomes a huge deal. You have to like be able to anticipate what other people around you are going to do. We do this all the time when we drive and when we navigate crowds and all this kind of stuff, but it's extremely hard to do in an autonomy stack. And it's a big sort of, at its core, that's an optimal control problem. It becomes a game theoretic control problem, which are very cool and have a long history. So these are all, I don't know, kind of fun areas to look at, cool areas to poke around at for projects in here potentially. And then also just cool things to look into if you're looking for research directions in general and like what to do with your life. These are all like big deal problems for the field. Cool. Yeah.
So by uncertain nonlinear systems, you mean completely, or is it like inaccurate problem?
I mean, any of the above. I mean, if I don't have a perfect model and or the system is changing in time, what do I do? And can I guarantee that I won't blow up and crash and kill someone? Yeah. All right, cool. Everybody, any last questions, comments, etc.? All right, cool. Let's do some more math. Hopefully that was enjoyable and entertaining. Okay, I think I can make this work. I think it is working. It's a little palate cleanser to give you a break from math because we're going to do more math now. If I can find my notes.
When we talk about model based, it's always a model based robot.
Yeah, well, it's a dynamics model. I mean, it's the combination of robot and world. You need to be able to like say, really, when we talk about model in the context of control, it means some set of math, that will tell you what the outcome of your control moves will be. It's basically something that can predict what's going to happen if you do certain control moves, right? That's what you need. Call it a simulator, call it a model, call whatever you want, right? I often find that there's a hang up on this terminology when you talk to RL people. They use the word environment and simulator for things that we would just call model. And then when I say model, they think it's something completely different than their simulator, but these are the same thing. So those are all the same thing. Yeah, it's basically a thing that will predict what's going to happen if you control the system a certain way, right? And then what we do, if you have that thing, what optimal control is all about is saying, okay, cool, now I'll take derivatives of that thing and use those derivatives to tweak my control to do something closer to what I want, right? That's what optimal control does. And RL basically does the same thing, but instead of taking derivatives, you do stochastic gradients and this kind of thing, right? But it's the same ideas, right?
So A and B comes from the robot and the world combined.
Yeah, it's literally A and B are just these linearized things, but that F, that's like, think of the F as your whole simulator. So it's whatever you need it to be for the task, right? Sometimes it means it's like, just F equals MA for like a quad rotor. Sometimes it's a model of like, some big humanoid and the box on the table and like, whatever it's got to pick up has to be in there, right? So it's a whole like kind of world model of like the local environment as well, right? It's whatever you need to predict the things you're trying to do. Okay, cool. Yeah, we use model, I think, in like the mathematical sense of, right, like a set of equations that tell you what's going to happen. And I think we're in business. Okay. I'm sorry, one sec. Here we go. Cool. Okay, so last time we sort of finished our discussion on constrained optimization, right? And did sort of augmented Lagrangian stuff. And what else? Kind of some merit function line search stuff. Basically that, right? And then today, we're going to dig into some control stuff. So we had our little control history talk. So today we're going to start talking about what I'll call deterministic optimal control, as opposed to, say, stochastic optimal control, which we'll talk about later. And what we're going to get to today are a couple of, we're going to go through a very classic result, which is Pontryagin minimum principle, which I feel like obligated to make you suffer through because it's one of the seminal results in the field, but we're probably not going to do much with, honestly, but you should know about it. I'm going to kind of like show it to you in a maybe somewhat non-standard way, but I think it makes sense. And then we're going to kind of introduce the LQR problem, which we'll spend a lot of time with, hopefully. So a linear quadratic regulator, which maybe some of you heard of, and is like, the seminal result in, kind of most of control theory. Okay, cool. So that's what we're going to talk about, see how far we get. As always, speak up if you have a question, because I'm often not seeing hands and stuff. Okay, so deterministic optimal control. What do we mean by this? So we mean, I'm going to write this down in continuous time first, but we're pretty quickly going to stop doing anything in continuous time and just talk about discrete time. But to give you sort of a flavor of what the general problem setup looks like, we're talking about in continuous time, minimizing over a state trajectory x of t and a control trajectory u of t. And we're going to minimize a cost function j that depends on x. And I'm going to write out the t's here to be very explicit about this. We mean trajectories for both x and u, right? These are functions of time. And this cost function has the following flavor. It's the integral from t naught to t final of some what we call stage cost, L of x u dt, plus some terminal cost, which we'll call L sub f, that just depends on the final state. So that guy subject to the dynamics, which looks like a constraint now. So x dot equals f of x u. And then also potentially subject to other constraints like torque limits, whatever else you've got, right? Okay, so let's label some things in here. Yeah. So this thing, okay, so these are state and input trajectories. This thing is called a cost function. This thing is called your stage cost, or sometimes one step cost or step cost. This thing is called your terminal cost. So, the terminal cost might encode just like, did you get to the goal kind of stuff, right? The stage cost can include things like, fuel or energy use or whatever, that kind of thing. This is your dynamics constraint. So we all know what that is at this point. Cool. Any questions about that setup? Okay, so that's it. Now the whole rest of the class is basically how you solve that thing in various, flavors. So one thing that's worth pointing out that I think is just a weird, kind of semantic thing that people talk about. So this is technically an infinite dimensional problem. And I will explain, you'll hear that thrown around, and that's sort of like what this calculus of variations stuff is all about. And I want to kind of just explain in some detail what is meant by this infinite dimensional thing. So it seems weird, right? That like, I don't know, if I evaluate X, like X is, in Rn, right? It's whatever the state space dimension is, that's fine. U is, X and U are both finite dimensional vectors, but X of t and U of t are trajectories in time. So they're continuous functions of time. So I want to be super clear about what's meant by this infinite dimensional business. So here's what it means. If I imagine taking, so let's talk about U for argument's sake, why not? Okay, so let's say this is U on the vertical axis and this is T, U of T. So this is some wiggly curve, right? So it can do whatever. It can, who cares? That's U of T. And so what I would typically do, right, if I want to, put this thing in a computer or whatever, is I'm going to sample this thing at a whole bunch of points, right? So I might sample it here and here and here, kind of whatever. And so I'd have all these sample points, U sub k, right? So I'd end up with, let's call this big U, 1 to n equals all these little samples. So U1, U2, ... all the way to UN at the final time, right? So the sense in which this is an infinite dimensional problem or whatever is really what we're talking about is, you can think about U of t, the continuous function U of t, is this sort of like limit of this vector as I take the number of samples or the sampling period or whatever, as I take the number of samples to infinity on this finite interval. Right. So if my delta t is, I don't know, say I'm sampling at like 100 hertz here, right? If I go to a kilohertz, 10 kilohertz, 100 kilohertz, right? The continuous function U of t is in some sense the continuum limit of that sample vector, right? Where I've stacked up a bunch of samples. Does that make sense to everybody? Cool. So that's what I mean by infinite dimensional here. It's like basically imagine sampling this trajectory at a set of sample times. I just take the limit as that number of samples goes to infinity. And I get U of t where I can query it at any time, right? Okay. Not that crazy. So cool. So what we're going to basically do is always just reason about things in discrete time, where these things have a discrete number of sample points. Pretty much all the results we'll get. I'm not a mathematician, so I can say this. Pretty much everything we're going to do, we're just going to do it in discrete time. And like, you can always take a limit and get the continuous result. If you talk to like a real legit mathematician, like theoretician person, they will argue with that because there's all these weird corner case things that can happen. But practically speaking, in real life, those corner case things never happen. So like, as far as I'm concerned, it's cool with me. We're going to be a little fast and loose with that. So that's why I think we're just going to do it all in discrete time. If you ever want the continuum result, take a limit and you basically have it. And we're kind of going to do that today with Pontryagin. Technically, people will argue with me about this. And like, I had a mathematician on my PhD committee who didn't like this, but you get the right answer. So I learned math from physicists, and this is basically what physicists do. So works for me. Okay, so that's that note. Some other notes, going back to this problem, right? What are the solutions to this problem look like? The solution to a deterministic optimal control problem is actually an open loop trajectory. It's just a trajectory, right? So if you don't have any noise and you know everything ahead of time, you have a perfect model, perfect simulator, right? And you're just trying to like, go like, dunk a basketball in the simulator, and it's deterministic and the same every time. The answer is just a set of open loop controls that you roll out in the simulator, and it works every time after that, right? There's no feedback, which is kind of an interesting thing. It turns out in the stochastic optimal control problem, because it's stochastic, open loop trajectories don't work every time anymore. So in the stochastic setting, the solutions are feedback policies, which is kind of interesting. And that's got hooks into like the way people think about RL. Okay, that's, yeah. Other notes, there are basically a handful of toy problems with analytic solutions here, but almost none of the cool ones have analytic solutions. Life is nonlinear, non-convex, and hard. So, you know, that. So we're going to really focus on numerical methods for solving this problem in general for nasty nonlinear versions. We're going to focus on discrete time. Sorry, I kind of said a bunch. Because that's how you get this into a computer, and how you are going to ultimately like build numerical algorithms to get, you know, solutions to these in general. Yeah. I mean, just U of t, just a trajectory, a set of controls that, you know, when you run on the hardware, you get the right answer. You get it to do what you want. So that only works, right, if you know everything perfectly. So if there's any uncertainty or stochasticity, if you just run those control commands, you know, the robot might fall over, might not end up where you want, right, in general. So that's kind of why I'm caveating this, right? Okay.
So when it comes to solution of trajectories, does it always like converge to like a unique trajectory, or
Nope.
there might be classic trajectories?
There might be what are so-called homotopy classes, right, of like equivalent trajectories. So the classic one is, you know, if I want to go from here to there and there's an obstacle dead center in the middle, I would get the exact same cost if I go around to the right or the left, right? So there's two like completely equivalent solutions to that. That happens all the time.
That's not like homotopy.
Yeah, like a fancy word for this are homotopy classes. So this means you've got like sort of multiple distinct solutions that like cannot be deformed into each other. So like the obvious example is obstacle. I can't cross through the obstacle, right? So these are distinct like branches of solutions, right? And that is extremely common. Okay, so let's write down the discrete time thing. Looks pretty much the same. So what we've got now, instead we've got samples x1 to n and u1 to n minus 1. We have the same cost function kind of deal, where it's a function of the whole sampled trajectory. But now instead of an integral, we just get a sum. K equals 1 to n minus 1 of, you know, stage cost xk uk plus terminal cost evaluated on xn. And now we've got our dynamics constraints, but instead of being x dot equals f of x, it's now the discrete time dynamics, which we learned how to do the first week. Xk plus 1 equals f of xk uk. And now we can have all kinds of constraints, right? So we could have, for example, torque limits that look like this. We might have, you know, obstacle constraints or whatever that kind of look like this maybe, which we've written down stuff like this before, right? When we talked about inequality constraints last time. So, you know, these are typically called torque limits, depending on the context. If you're doing flying things, this might be called thrust limits. And then this could be, you know, obstacle or safety constraints. And everything else is kind of the straightforward thing, right? So we basically, you know, turn the integral into a sum, discretize the dynamics using RK4, or pick your favorite integrator, and that's kind of what that looks like. Any questions about this?
So when we were doing like optimization and stuff, a lot of times like the solution would be like right on the boundary of
Yes.
the constraint. is it like, is that a common problem where like?
Happens
you're
all the time.
Okay.
Yeah, so it turns out you can prove that under certain cost functions and stuff, what happens a lot if you do minimum time. If you say, I want to get to the goal as fast as possible, the solution to that is almost always what's called a bang bang solution, which means you're full gas, full brakes, and you're just railing against the torque limits. That's super common. It's a property often of like the cost function that you'll get solutions like that. So if you ask for a cost function that's like get there as fast as possible, you'll get something like that. If you ask for a cost function that's like minimize fuel or energy or something like this, you'll often get like smoother solutions that are less aggressive. But yeah, if you write down like a cost function that's asking for something aggressive, you'll tend to get stuff like that.
So is the solution to kind of use both cost functions, but like have like a leading term between them, or?
You just write down whatever you care about. The cost function is what you care about, right? That's how you write down what you care about. So if you want something to go as hard as possible and get there as fast as possible, you write that down, that's what's going to come out. If you want something that's going to like be super efficient and smooth, write that down and you'll get something smooth and efficient, right? That doesn't rail your actuator limits and stuff, right? So it's that cost function is really like where design kind of comes into this. That's where you have to be smart and you have to like find a way to encode what you care about, qualitatively into that thing. Yeah, there's an art form to this, it turns out. And looks like that died. Come on. That's weird and not helpful. So any other thoughts, questions while I swear at my laptop under my breath and try not to, put it on the internet for posterity?
So the typical approach to essentially, like no system is deterministic, right? So are we do
Well-
essentially pretend it's deterministic to get like a nominal trajectory and then?
I would argue that like most robotic systems are pretty deterministic. Like if you, there's a difference between stochasticity, right? Like being non-deterministic and being uncertain, right? So when we talk about robots, there's usually uncertainty in the model parameters or unmodeled things or whatever. But if you go run the same experiment twice, you're going to get the same answer out pretty much with very high, confidence. Like it's basically going to do the same. If you put the same motor commands in, it's going to do the same thing, right? So they're not stochastic in the sense that the results of your inputs are uncertain and like you're going to get different results experiment from experiment. There may be uncertainty in there that you just don't know what the parameters are, but there's some like kind of deterministic model of the thing, right? That's not always the case. There definitely are legit stochastic control problems, but I would argue most of the control problems in robotics are deterministic. Anything else on that?
The stochasticity comes from the modeling the robot and then like on the world as well.
I mean, this gets into some like weird philosophical territory that like we probably don't want to go into really, but like the stochastics thing means that like if I run the same exact experiment n times, I'm going to get n different results, right? Like it means that like if I have a robot sitting here and I put in the same commands, like have it walk over there, I do that a few times, it's gonna look, the answer is gonna be different every time, right? It's like rolling a dice, right? That's a stochastic process, right? So that's what we're talking about here. We're saying if I run the same control commands on the same hardware multiple times, will I get the same result, within some tight tolerance every time? And I'd argue most of the time in robotics, that is the case. If that weren't the case, we'd have a whole different, things would be very different if that were not the case, right? In general. So I'd argue we mostly live in a deterministic world. There are for sure stochastic problems, but most of the stuff we do is not that. Yeah.
So you would say it's like deterministic evolutionary in the dynamic.
Yeah, I mean, it basically comes down to, can I simulate the thing? Like, is there some, it's like, is it repeatable? Is it simulatable? This kind of thing, right? That's what it means. It's when we talk about a good proxy for stochasticity is noisy. Is it noisy? If I do the same thing on it 10 times, do I get the different results every time? Right. Does that make sense? Okay. Cool. So discrete time, blah, blah, blah. And I think things are working again, which is good. Okay, so things to note. This discrete time version, this is now we talked about the continuous version was an infinite dimensional because of these U of t, X of t things. This guy is now finite dimensional. There are only there are a discrete finite number of time steps n, right? And that's the whole problem, which is good for a computer. What else? Quick note on terminology. The samples in this guy, so these XK, UK samples, we often call these, it's a term of art, I guess, in the field. We call these knot points a lot. So if you hear me say that, that's what I mean. I think that term comes from splines, which are often used to like discretize trajectories. But it's just like a super common term you'll hear everybody use. So don't get confused on that. What else? Yeah, so notes on converting between continuous and discrete time. We go from continuous to discrete time. Using an integrator, right? Like a Runge-Kutta method. So both integration on the dynamics, which corresponds to some kind of Runge-Kutta thing, and integration on the integral, right? I got to integrate that integral cost function, which is called the quadrature rule. It's the same thing. Yeah. This is kind of, we're being a little fast and loose with the language, but yeah, we mean like the discrete time points you're evaluating the dynamics on in your trajectory. Runge-Kutta, et cetera, that kind of stuff. And then if we solve this discrete problem, in the computer, we often want to go take that discrete answer and then like convert it back to a continuous thing to like run on hardware, upsample it, whatever. And so we can do that too. And that's is interpolation, right? So this is why we often use splines or whatever to represent trajectories, because often we'll get the answer with like a very small number of knot points, and then we'll maybe want to query that at a much, much higher sample rate when we go send the commands to the motors, whatever. We do that by interpolating the solution using a spline or something. Okay, cool. Any questions about this? This is like setting the stage. This is the stuff we're going to do. Okay, so now we're going to get into, and hopefully get through, Pontryagin minimum principle. Okay, so fun fact, this is also very commonly referred to as the maximum principle. Anyone have any idea why? You got it. It turns out it's not just them. The original like Russian papers on this were maximizing a reward instead of minimizing a cost. So it actually historically has been both. It's not just the RL people. Some old school control people from the 50s apparently also like maximizing. So doesn't matter. Just stick a minus sign on it. You can flip max to min or whatever. Okay, so what these things are, who's heard of these before, by the way? Like, not that many. Okay, so these are the first order necessary conditions, which, hey, that sounds familiar. For a deterministic optimal control problem. So there's a strong hint in there on like what these things are and what's going to happen now. These are basically just a restatement of the KKT conditions that we know and love, but in the context of this problem we just wrote down. So it's literally going to be, I'm going to write down the KKT conditions for that optimization problem, but there's a lot of massaging and inventing of new things that shows up in this to get to like a cutesy little, tight result. It's kind of nice. So yeah, I'll say that what I just said is particular to the discrete time setting. So in discrete time, just a special case of KKT conditions. In continuous time, it is a little more involved to derive and like little weirder, but I would say all the weird stuff is not to be concerned with unless you're a very finicky mathematician type, and doesn't really matter for us. So let's do it. So yeah, these are just KKT conditions, but I think this is kind of exposing, they're just the KKT conditions for the problem I wrote down, that deterministic problem. But they basically, this is your first foray into like a theme that's going to come back over and over again, which is exploiting problem structure. These optimal control problems are not just generic optimization problems. There's a lot more going on in there. There's structure in that problem that you can exploit when you develop algorithms. So this is the first hint at like what this structure looks like, and the fact that these aren't just KKT conditions. There's a lot more meat inside there. This is basically like digging into the KKT conditions we worked last time and looking at the structure of the optimal control problem. So hopefully that'll be clear as we do it. So here we go. We have our problem. I'm going to write down like kind of a simple version of this. So just the cost and the dynamics constraints. We won't look at any other constraints right now, though this is extended pretty straightforward ways to handle other constraints. So we got this, we got discrete time dynamics. We're going to now write down the Lagrangian, which we know how to do. Right, so Lagrangian, I'm going to take the dynamics constraints and move them up into the objective with a Lagrange multiplier. So there we go. And I'm going to keep this, the thing that we're going to keep doing, right, is carrying around this sum over time steps business, right? But this is just straight up Lagrangian like we did before. So I've got the cost function stuff, and now I'm going to pick up this Lagrange multiplier term. And importantly, I'm going to index this in time. And this is kind of an arbitrary choice, but I'm going to put a k plus 1 on there. Could have put a k on there, it doesn't really matter, but I'm choosing to line it up with the xk plus 1 in this dynamics constraint. Cool. So this is exactly the stuff we did last time. The only difference is I'm basically, summing it up over time steps, right? So it all kind of is in this weird sum thing. Now we're going to make something up that's going to come out of nowhere that may make sense if you've done some like graduate level physics-y stuff before later, but right now will make no sense and honestly isn't very important. It's just a made up thing with some deep connections to classical physics, if you care. So we often state this, this result is stated in terms of this thing called the Hamiltonian, which I will just define for you right now, which is connected to the classical mechanics, Hamiltonian mechanics stuff, but that is not important if you haven't seen that before. It's just this random made up function. So literally what it is just the thing inside the sum in the Lagrangian. So it's the cost, the one-step cost or stage cost, plus the Lagrange multiplier term with the dynamics. Cool, that's it. We're just making this up. Yep.
Even like different co-location points, like even though you're kind of like in the same task, how different can your cost, like eventual cost be? Like, would your choice of co-location points dramatically
So
influence your outcome?
ultimately we want to solve the continuous problem, right? So if that's happening, it means probably your discretization is bad. So one thing you can do to check this is so-called mesh refinement. So you'll like solve it with a coarse mesh, coarse discretization, then add some more knot points and like upsample and resolve. And if those answers are very different, it means you probably need a finer discretization and that your discretization wasn't fine enough to really like capture the flavor of the original problem.
But if you shift your co-location point like back and forth a little bit,
No, it shouldn't, right? You don't want it to. So if that is happening, it means you probably need to take more sample points and that your mesh was too coarse, right? Okay, cool. So this thing, now what we're going to do is just take that definition and plug it into the Lagrangian that I wrote down. So here you go. And I'm going to play a little indexing game, which I'll talk about in a sec. So here's, I'm going to pull out the first time step outside the sum. And then I'm going to like re-index the inside of the sum, starting at 2, for kind of weird reasons that don't make sense unless you really like pay attention. You probably should just do this yourself if you really want to understand what's going on here. So I'm mostly going to show you this isn't that scary. And like all the derivations of this in books, in control theory books, are awful. Like super, they all do it in continuous time with a bunch of like calculus of variation stuff, and it's super, super hard to understand. So I'm trying to show you that it's not that scary, but there are some little twists and turns in this that are, this being the main twist to the derivation. So what I did was pull out the first time step, right? X1, U1, lambda 2, and then kind of re-index the stuff inside the sum. And then I end up with, I'm pulling out, so the terminal cost is not in there, right? Obviously. And then it turns out I also pull out this terminal dynamics constraint term as well. Okay, so like if I look in the sum, right, to be clear, I'm pulling out the first time step on the left, and then on the right, I'm pulling out the last lambda x thing. What that lets me do is re-index the inside of the sum. So I start at k equals 2 now. And the reason I did this is to make the lambda k xk, the thing on the right where the Lagrange multiplier is, I did this trick such that I could have those indices match up with the ones inside the h. That's why I did it. This is not, and I did it specifically so that I could, because what I'm going to do next is take gradients of that thing with respect to uk and xk, and I wanted the time indices on the thing in the sum to be all the same for when I took the gradients. It just cleans up the rest of it. Yeah.
Sorry, it's something. Where did the last lambda transpose times xn?
Mhm.
Where did that come from?
It's just the last term in this sum.
The original sum went up to n minus 1.
Yep,
right?
but it's an xk plus 1 in there.
Oh, okay.
Makes sense? So yeah, there's some details in here you got to pay attention to. So like, honestly, if you care, I highly recommend like sitting down and working this out yourself, like without looking at the notes or whatever, if you want to like really grok it. There's some like little twists that it's not, I'm telling you why I did this, but like until you like really stare down and do it out yourself, like it's not going to, these little details aren't really going to make a ton of sense. Incidentally, there's a fun discrete continuous thing here. This index game I just played, if you do this in continuous time, it turns out it's integration by parts, which is not at all obvious. Again, you should play these games and check it out for yourself if you care. I'm here to show you the path, but I cannot make you walk the path. So again, if you really want to know this and understand it, you should definitely do it yourself. Okay, cool. So now we're going to do the obvious thing. That was like the one like weird definition trick, and indexing trick was weird. Now I'm literally just going to take grad respect to x, grad respect to u, grad respect to lambda, set them all equal to 0, and that's it. That's all it is. So it's not scary. It's just this definition of this weird Hamiltonian thing that comes from nowhere. You don't need to worry about. And then it's just KKT conditions like we did before. So I'm going to do the x and lambda first. So here we go. Partial L, partial lambda. Let's do, we'll do lambda k first. So if I just look at that thing and take the derivatives, I'm going to get partial h, partial lambda k minus xk plus 1. And that, if what it better be, right, is going to just end up being the dynamics constraints, right? That's what happens when I take partial of my optimization problem with respect to lambda, just gives me back the constraints, right? We did that before. So here, the only constraints are the dynamics. So if I take partial with respect to lambda, I just should get the constraint back. And I do, if I go look at that. So that's good. Checks out. That equals 0. Okay, now I'm going to take partial with respect to x. And I'm going to get partial h, partial x minus lambda k transpose. And if I like expand that out, you're going to get the following thing. So it's gradient of the cost with respect to x plus some lambda stuff times the dynamics Jacobian, and then this next lambda. I'm just expanding this out so you can see it. And then, so I have to take the derivative with respect to all the x's, and it turns out, right, there's this xn hanging out at the end. So I got to do that one sort of special cased. So we'll do that. So partial L partial xn equals just gradient of the terminal cost with respect to xn minus lambda n transpose, right? That's just that last term. Cool. Okay, so that's it. That's all it is. And then notice I didn't take the derivative with respect to u yet. And this is for a very specific reason, which shows up all the time. And this is the kind of the standard move. So for u, we're going to actually just special case it and write out the min over u explicitly. The reason is because torque limits are so common that if it was unconstrained, I would actually just have partial L, partial u here. But you usually special case the u and write it down the following way so that you can handle torque limits. All right, so we get UK equals argmin over, we'll write it as u tilde here to just emphasize, that it's the u, the real u is the optimal u tilde here. Of that Hamiltonian guy subject to u tilde this is sort of this funny set notation. This just means u tilde is in the set of feasible u's, which typically just means obeys torque limits or whatever, right? So let me write that down. So this would, correspond to, potentially just the box limit case like we wrote before, which is the most common. But could mean, other things, right? It could mean, thrust cones or whatever, right? All kinds of stuff. Okay, so that's the whole thing. I'm now going to write out like the summary version of it all together. And if you've ever taken the physics, if you know about the physics Hamiltonian, this is where that sort of connection shows up. And is ultimately why we define this Hamiltonian thing. It's that it makes the results look neat and clean. So if I'm just going to rewrite this stuff now in like clean shorthand, it turns out you get the following thing. xk plus 1 equals grad with respect to lambda of h. Lambda k equals grad with respect to x of h. And then UK equals argmin over the u tilde thing of h xk u tilde k plus 1 subject to u tilde being feasible. Cool. And then the last thing is we get this lambda n term that's sort of special cased, which is this. So the reason I wrote it out like this is, has anyone done Hamiltonian mechanics and see the connection there? Looking at you, Aaron.
Yeah.
The first two lines are Hamilton's equations, and lambda is the momentum.
Oh, yeah.
Don't worry about it. Sorry to, if you were napping there, it's totally okay. I don't mind. Okay, so that's fun. Okay, so here's the interesting thing about this. The top line is literally just the dynamics, right? Like we already did that. That's what falls out of that. But it so that goes forward in time, right? It's xk, plug in xk, uk, get xk plus 1. The second line is some other equations, right, that we wrote out before. But what direction do those go? Look at the lambdas. I got lambda k on the left, and I got lambda k plus 1 on the right. That one goes backwards in time. So this sets us up for some interesting stuff. And then the last one, yeah, whatever. Don't worry about that too much. But the important thing is that the x stuff goes forward in time, and the lambda stuff goes backward in time. And we get boundary conditions. So like I start at some initial state that I know, right? So I know X naught, and I have a forward equation for that one. The lambdas, I have a boundary condition at the final time based on my terminal cost. So I know lambda n at the final time, and I have a set of equations for going backward on that one. So this is kind of weird. And this is actually, who's heard of a shooting method? Maybe. This is where shooting methods come from. You have to shoot forward with your dynamics and backward with your lambdas, and somehow get these to match up in the middle. So this is like where shooting methods come from. What else is there to say about this? Oh yeah, so we can restate. I'll write you the continuous versions of this, continuous time, which you can get from taking a limit. Don't tell the mathematicians. And they look exactly the same. So there's no surprises. And we'll kind of call it there, because I know we stop at 6:20 now. Here you go. So in continuous time, this looks like you get ODEs for these things, but they're otherwise the exact same kind of thing. So yeah, no surprises. They look exactly the same. You just get, dots and ODEs instead of, Ks and K plus ones or whatever, right? And the second one goes backwards in time. That's what the minus sign on the lambda dot means, right? Yeah. Up here. I'm just taking the derivatives of this thing right here. Yeah, whole thing. X, lambda, all the stuff. Yeah, it's partial L, partial lambda K. Yep. Yeah. So I literally, it's just taking the gradient of the Lagrangian with respect to everything, just like we did before to get KKT conditions. So it's nothing special. I'm literally just taking the gradient and setting it to 0. Just I have a lot of things to take the gradient with respect to here. So I'm writing those all out kind of separately.
There are no limit for states.
I'm not here. I didn't write any state constraints here.
If we have, then also get Prontryagin.
Yeah, then you'll get more constraints, more Lagrange multipliers. And it turns out, yeah, that's kind of hard to do in this setting. It's annoying.
So do we do argument in that case, or do we?
No, you would get another set of like, you get another constraint with another multiplier. That'd be the way to do that. Yeah, this argument trick only works for control limits, which is not obvious, but trust me, you can't do it for obstacles. Turns out obstacles are kind of hard in this setup and are pretty bad. And probably your best bet if you were doing something like this is to use penalties, which are bad also, but kind of the best way to fit things into here. Okay, so there's that. Yeah.
So lambda here are Lagrange multipliers.
Mhm.
Do they bear some physical meaning?
They do indeed. And it's going to take us another lecture or two to get to that.
So that if those are like forces or whatever, like then that means you can't step it in arbitrary. Right?
Yeah. Yeah. You can think about them. There's a very, very kind of like nice interpretation of them, but it's going to take us a while to get there. And like next week, we'll get there. Cool. So yeah, I'm happy to hang out. We're at time. I'm just going to write some of these things down that I've been saying out loud. So feel free to hang out, ask questions, whatever. So I will say these out loud too, if I didn't already. This is, yeah, I said this is shooting methods, which I'll just now write some notes about. Many algorithms are based on this stuff. If you're all here anyway, I'll say it out loud, but you can leave. So back in the day, like i.e. Apollo days, Pontryagin, Russian space program days, people actually used these continuous ODE versions and solved these things by solving the ODEs forward and backward and alternating a whole bunch, which are called shooting methods, which are actually basically gradient descent in continuous time. In fact, this is extremely closely related to backpropagation in a neural network. Has anyone heard of neural ODEs and these kind of things? Like this is that. That's what this is, where your dynamics is your neural ODE. This is what you get in those things, which is kind of fun. Cool. You guys can leave. To be clear, I'm just going to write like a couple little bullet points and we're done. But I'm also so those things suck though. Don't do them.
Back when I did a shooting method in the lab, I was like trying to solve a boundary value problem.
Yep.
And like changing it from unit, so I did bisection and actually solve that.
Yeah, bisections, you can only really do that though on like 1D problems, right? So this is a boundary value problem where you have x naught and lambda n,
Mhm.
and you gotta integrate the ODEs like back and forth until
Oh, I
you
see.
get them to match up, which is a pain. And the standard approach is you integrate these back and forth, and basically the integrating these ODEs back and forth and just repeating that over and over again, it does gradient descent on this guy. Essentially, I'll show you this on Tuesday. We're gonna do it, and then show you that it's bad and that there are better things to do. Other fun fact, lambda is called the co-state sometimes. Okay. Yeah, questions are good. I'm just gonna finish writing this.
Yeah, I really have questions on, the optimizations.
Okay.
Does for your physical forces or moments.
Um,
How do you actually deal with it, like when it comes to optimization?
we will talk about this.
Can I get a sense now?
Maybe. I'll give you some hints. You're really burning. That's it, I promise. Cool. Shooting methods, they're not good. Don't do them. End of class. Next time we'll talk about LQR, and I'll do shooting method on LQR and you'll see how bad it is. Thank you.